Extending Molecular Simulations for Liquid and Soft Matter by Hayato Shiba at the University of Tokyo. I joined the Supercomputing Research Division at ITC, the University of Tokyo, about half a year ago. I have been engaged in studies of soft and liquid matter. My scientific targets are, for example, soft materials including polymers, colloids, and biomembranes, or liquids in a broad sense including water, ionic liquids, and glasses. Liquid and soft materials are largely deformed by mechanical stresses, or structurally altered by thermal fluctuations. Large-scale fluctuations and slow dynamics are often essential, so I have been making efforts to let my simulations cover a broad range of spatiotemporal scales. HPC is an essential tool for this purpose. Here are examples of my present and previous research targets. Recently, I am shifting my research target to electrolyte solutions, where a small amount of ions are solvated in water. In dilute electrolyte solutions, a small amount of ions cause drastic effects on their macroscopic properties, via an interplay with the water environment surrounding them. Such a coupling between micro and macro scales via many-body interactions among water molecules is not only interesting in itself, but also it has been extremely difficult to examine the validity or possible extensions of existing physico-chemical theories by using molecular simulations, because these theories are for the dilute limit, that is, concentrations around millimolars, which have been difficult to simulate directly by MD simulations. Under this situation, I am beginning to make two different types of efforts. One is to extend the atomistic molecular dynamics to micrometer scale air-water interfaces to directly cover the long wavelength phenomena, by using the present state of the arts in HPC. The other is to develop a method to capture long-time phenomena, and I take ion pairing, or unpurling, phenomena in water as a target. Ion pairing, or unpairing, is a typical slow process that takes longer than milliseconds. It is not expected to become possible to perform molecular dynamics over such a time scale, that is, over trillion steps in all atom simulations, because of the expected end of Moore's law and of the communication wall problem. One way for investigating longer time dynamics by molecular simulations is to sample the trajectory precisely on the transition paths without the bias, and then to run the molecular dynamics along these paths. Here, we need to find an appropriate collective variable, or reaction coordinate, that characterizes the transition paths in the energy landscape. If we cannot find such reaction coordinate, otherwise we cannot be free from the sampling biases. I am now making an effort to develop computational methodologies to identify such a reaction coordinate semi-automatically by using the machine learning algorithm. Thank you for listening to this video.